Welcome to all to Physics Department. I am Ramakrishna BN, Assistant Professor of Physics, Government College for Women, Mandya. Dear students, today is my first class, first online class. See, all of you know about the syllabus, first semester physics syllabus, paper 1. The title of the paper is Mechanics, Properties of Matter and Radiation. See, in this paper, you have two parts, part A and B. So, I am going to handle 3 chapters from part B. So, they are conservation of energy, viscosity, surface tension. See, first of all, conservation of energy. I am going to start conservation of energy. So, this is the 4-hour syllabus. See, in this conservation of energy chapter, so we have to discuss a few concepts. First concept is conservative force and non-conservative force with examples. See, to understand the conservation of energy, so you should know about some basic ideas. So they are work done. What is power, work done, energy? Say work done. Work done means work done is nothing but the force into displacement. All of you know that you have studied it in your PU classes and all. Work done, amount of work done is nothing but force into displacement. Suppose here there is a particle which is moving from point A to point B, then to move from initial point A to final point B, the total amount of work done is nothing but W equal to integration from A to B, force into displacement. So similarly, power. So what is power? Rate of doing work is known as the power. That is P equal to dW by dt. So W is the amount of work done, P is the power. Then rate of doing work, that is P equal to dW by dt. But we know that work done is nothing but the force into displacement, F into dr. So therefore, power is nothing but force into velocity. We can say that P equal to dW by dt or is equal to F into dr by dt or is nothing or equal to F into V. Force into velocity is nothing but the power, instantaneous power. See, the average power is amount of work done by time. Average power equal to W by T. And also you should be knowing what is energy. See, energy means the capacity to do work is called the energy. The capacity to do work is called energy. The energy is classified into two, kinetic energy and potential energy. So what is kinetic energy? The energy possessed by a body because of its motion is called kinetic energy. Suppose if a particle of mass m is moving with velocity v, then kinetic energy of the particle is equal to half mv square. M is the mass, v is the velocity of the particle. Kinetic energy equal to half mv square. Then what is potential energy? The potential energy is nothing but the energy possessed by a body because of its position. The energy possessed by a body because of its position. Okay. So this is denoted by the letter U. See, this potential energy measured by the amount of work which is done in moving a body from one point to another point. Usually, the standard reference point is taken to be infinity. Therefore, potential energy is defined as the amount of work done in moving a particle or any body from infinity to a given point whose position vector is r, vector r. Therefore, potential energy U is equal to minus integration from infinity to r, F into dr. So here minus because this indicates work is done against the force. Okay, so these are some basic points related to work, power, and energy. So now come to the conservative and non-conservative forces. So as per your syllabus, so you have the first concept in your syllabus. In chapter conservation of energy, first concept is conservative and non-conservative forces. So we have to discuss these concepts, two concepts with examples. Okay. See, let us first we will discuss about what are conservative forces. You can see conservative force. A force is said to be a conservative if the work done by it in moving a particle from one point to another point depends only on the end points. So this is very important. Depends only on the end points and not on the path followed. Okay. It depends only on the end points. See, if you look at the diagram, okay, see, suppose there are 2 points A and B, and there are 2 paths P and Q. So there is a particle which is at point A is moving to reach point B on a path P. There is one more path Q. You can look at the diagram. Okay, simple diagram. So there is another path Q. So there is a particle A is moving along the path Q to reach the point B. So there are 2 paths here. One is APB and other one is AQB. So therefore, as per the definition of conservative force, so it depends only on the end points. End points means so A and B. That's all. Not on the path. APB is one path. AQB is another path. It does not depend on the path followed. Okay. If a particle is taken from point A to point B through APB path or AQB path, that is, okay, AQB path. Each time the work done by the force is same. So that is, if integration A to B, force into displacement, is equal to integration A to B, force into displacement. See, one is the amount of work done along with APB path and other one is along with the AQB path. Okay. So both are equal in case of the conservative force. Both the amount of work done, okay, so are equal. Then the force F is a conservative force. The region in which a particle experiences a conservative force is called conservative force field. Field is a region, okay, is area or a region in which particle experiences a conservative force. Then examples. What are the examples for conservative forces? See, central force is a conservative force. Because we know that conservative force means it depends only on the end points, not on the path followed. Therefore, central force is the best, one of the best example. If a force acts on a particle in such a way that it is always directed towards or away from a point, and its magnitude depends only upon the distance from the point. Then this force is called a central force. See, central forces are gravitational force, electrostatic force, elastic forces. So they are all the example for the conservative forces, because all these forces depends only on the end points. They are not depending on the path followed. So another force, non-conservative force. Okay. So what are non-conservative forces? See, non-conservative forces are the reverse process of the conservative forces. A force is said to be conservative, non-conservative force if the work done by that force on a particle to move it from one point to another depends on the path taken. Here, path is very important. Okay. But as in case of conservative force, only end points, depends only on the end points, not on the path followed. But in this case, okay, so it depends on the path taken or path followed. Therefore, integration along with APB path and along with the AQB path, the total amount of work done along with different paths are not equal. Therefore, integration from A to B, force into displacement along APB path is not equal to integration from A to B. So work done is not equal along with the AQB path, both are not equal. So then, if they are not equal, the total work done along with different paths are not equal, then such a force is a non-conservative force. Frictional force, viscous force, so they are all the non-conservative forces because they depends on the path followed. See, for a conservative force, the work done around a closed path is always 0. Okay, you should be knowing that for a conservative force, the total the work done around a closed path is always 0. So these are some of the points related to conservative and non-conservative forces with examples. So there is one more concept as per your syllabus: conservation of energy in a conservative force field. How to calculate the conservation of energy? How to calculate the conservation of energy in a conservative force field? Because we know that conservative force field is nothing but the region in which a particle experiences a conservative force. So field, conservative force field means that is the area or a region where the particle experiences a conservative force. Then how to calculate the conservation of energy? See, let a particle of mass m move from one point to another under the action of a conservative force. Consider a particle as mass m, okay, which is moving from one point to another point under the conservative force. Okay. Then the amount of work done. How to calculate the amount of work done? We know that work done is nothing but the force into displacement. Okay. To reach the particle from point 1 to 2, so the total amount of work done is W equal to integration 1 to 2 force into displacement. If the particle is moving with velocity v, then according to the Newton's second law of motion, F equal to ma or m into dv by dt. Therefore, work done. So substitute the value of F, okay, for work done. Therefore, work done W, total work done W equal to integration 1 to 2. So F means m into dv by dt. Then, if you simplify that equation, just rearranging the terms, dv into dr by dt. So that is equal to m into integration 1 to 2 v into dv, where v is dr by dt. Velocity is nothing but rate of change of displacement. So therefore w is equal to m into integration of v is v square by 2. So limit from 1 to 2. Okay. So by integrating of, just apply the limit, upper limit and lower limit of m v2 square minus of m v1 square. If of mv square is nothing but the kinetic energy of the particle, then the total work done or the amount of work done to reach the particle from point 1 to 2. So w equal to k2 minus k1. K2 is of m v2 square, k1 is of m v1 square. Both are kinetic energies. Okay. Change in kinetic energy. A2 minus k1 is nothing but the change in kinetic energy of the particle. See, from the definition of potential energy, we know that U is nothing but minus integration infinity to r f into dr. Therefore, f means du by dr. Okay. So therefore, amount of work done w equal to integration 1 to 2 f into dr. So the definition, the general definition, force into displacement for work done. So f into dr is nothing but du from the above equation, because f equals du by dr, or du is equal to f into dr. So by integrating and applying the limits, so you will get u2 minus u1. Integration of du is nothing but u. So apply the limit 1 to 2. So u2 minus u1 is nothing but change in potential energy. Therefore, so from equation 1 and 2, so equation 1 is w equal to k2 minus k1. Equation 2 is nothing but w equal to u2 minus u1. Okay. That is, the amount of work done is nothing but change in kinetic energy of the particle is also nothing but the equal to change in potential energy of the particle. So therefore, from equation 1 and 2, w equal to k2 minus k1 is equal to u2 minus u1. By rearranging, k1 plus u1 is equal to k2 plus u2. That implies k plus u, sum of the kinetic energy and potential energy, is always constant, because if for two particles, okay, for at 2 points, there is a particle reaching from point 1 to 2, okay. So then the total kinetic energy is k1 plus u1. Total kinetic energy at the point 1 is equal to total kinetic energy at the point 2. So that is nothing but k1 plus u1 is equal to k2 plus u2. So therefore, generally k plus u is always a constant. This means that the sum of kinetic energy and potential energy of a particle remains constant at any point in a conservative force field. In a conservative force field, if you calculate the kinetic energy and potential energy at a point, so the sum of kinetic energy and potential energy is always a constant. This is the law of conservation of energy in a conservative force field. Okay. So what we conclude is k plus u is always a constant. That is, the sum of kinetic energy and potential energy of a particle remains constant at any point in a conservative force field. So these are the points related to the conservation of energy in a conservative force field. So next class, so we will discuss about the applications or illustrations. We can say that illustrations So there are two illustrations: vertical oscillations of a loaded light spiral spring and calculation of escape velocity in the gravitational field of the earth. Okay, so these are the illustrations for the conservation of energy. So we will discuss in next class. Okay, thank you.